In the present video, we will discuss a example problem of Big M method. Let's see the problem. Show how the Big M method will conclude that the following problem has unbounded solution. Maximize z equal to 3x1 plus 5x2 subject to the constraint x1 minus 2x2 less than or equal to 6, x1 less than or equal to 10, x2 greater than or equal to the 1 and x1, x2 are the greater than or equal to the 0. While determination of optimal solution, if all the values in the key column are negative, which is the indication of unbounded solution. Let's see the solution. First step is convert the general linear programming problem into standard linear programming problem. For this we have to introduce the positive slack variable, that is plus s if the constraint is having the less than or equal to inequality symbol, and introduce the negative surplus variable and positive artificial variable, that is minus s plus a if the constraint is having the greater than or equal to inequality symbol, and introduce only positive variable, that is plus a if the constraint is having the equal to symbol. In the given constraint, first constraint is having the less than or equal to symbol, so we have to introduce the positive slack variable, that is plus s1 in the first constraint, and in the second constraint is also having the less than or equal to symbol, so we have to introduce the positive slack variable s2 in the second constraint. Third constraint is having the greater than or equal to inequality symbol, so we have to introduce the negative surplus variable and positive artificial variable, so that is the minus s3 plus a1 in the third constraint. Then given constraints will become the x1 minus 2x2 plus s1 equal to 6, x1 plus s2 equal to 10, x2 minus s3 plus a1 equal to the 1. Then we have to reformulate the given objective function in the terms of the decision variables, slack variables, surplus variable and the artificial variable, that is maximize z equal to 3x1 plus 5x2 plus 0s1, 0s2, 0s3 minus ma1. Here cost coefficients for the surplus variable and the slack variables are the 0, and for the artificial variable cost coefficient is the minus m. And here x1, x2, s1, s2, s3 and a1 all are the greater than or equal to the 0. Second step is the find the initial basic feasible solution. For this, consider the basic variables, that is x1 and x2, and surplus variable s3 are the 0, and introduce these values in the constraint equation. Then we will get the s1 equal to the 6, s2 equal to the 10 and a1 equal to the 1. So this is the initial basic feasible solution. So next step is construct the initial simplex table. So this is the our initial simplex table. Here b is the basis variables. Our initial basic feasible solution is the s1 equal to 6, s2 equal to 10 and a1 equal to the 1. So s1, s2, a1 are the basis variables. So I have to write down the s1, s2, a1 are in the column B. And CB is the cost coefficients of the basis variables. So s1 cost coefficient is the 0 and s2 cost coefficient is the 0, a1 cost coefficient is the minus m. So write down these values in the CB column. So that is 0, 0 and minus m. Next xb is the initial basic feasible solution, that is s1 equal to the 6, s2 equal to the 10, a1 equal to the 1. So write down these values in the xb column. And cj is the cost coefficients for the respected variables. So for the x1 cost coefficient is the 3 and for the x2 cost coefficient is the 5, and for the s1 cost coefficient is the 0, and for the s2 cost coefficient is the 0, and for the s3 cost coefficient is the 0, and for a1 cost coefficient is the minus m. So next we have to write the x1 column. So x1 column is the coefficient values of the x1 variables in the first constraint, second constraint and the third constraint. In the first constraint, x1 coefficient value is the 1, and in the second constraint x1 coefficient value is the 1, and in the third constraint x1 coefficient value is the 0. So write down the 1 1 0 in the x1 column. Similarly for the x2 column, so minus 2 and 0 and 1. And for the s1 column, so 1 and 0 and 0. Similarly for the s2 column, so here in the first constraint there is no s2, 0 and 1 and the 0. And for the s3 column, so 0 0 and minus 1. And for the a1 column, 0 0 and 1. Next step is the calculate the values of Zj minus Cj and check the basic feasible solution for optimality. So first I have to determine the Zj minus Cj for the all the variable columns. So here Zj minus Cj equal to the summation of Cb into Xj minus of Cj. So first I have to determine the Zj minus Cj value for the x1 column, that is the first column. So Z1 minus C1 equal to the CB x1 minus C1. This value equal to the 0 into 1 plus 0 into 1 plus minus m into 0 minus 3, which is equal to the minus 3. Next to Z2 minus C2 for the x2 column, that is the 0 into minus 2 plus 0 into 0 plus minus m into 1 minus 5, which is equal to the minus 5 minus m. Next to Z3 minus C3 for the S1 column, that is the 0 into 1 plus 0 into 0 plus minus m into 0 minus 0, which is equal to the 0. Next to Z4 minus C4 for the S2 column, which is equal to the 0 into 0 plus 0 into 1 plus minus m into 0 minus 0, which is equal to the 0. Next to Z5 minus C5 for the S3 column, that is the 0 into 0 plus 0 into 0 plus minus m into minus 1 minus of 0, which is equal to the m. Next to Z6 minus C6 for the A1 column, which is equal to the 0 into 0 plus 0 into 0 plus minus m into 1 minus of minus m, which is equal to the 0. So here Zj minus Cj values are the 3, minus 5 minus m, 0, 0, m, 0. Among these values, most negative value is the minus 5 minus m. So this one is the most negative value. Then you have to select this value, and respected column is the x2 column. So x2 column is the, we are calling as the key column, and respected vector, that is the x2 value is incoming into the basis. So x2 variable is enter into the basis. Next step is calculate the minimum ratio of xp divided by ck. Here ck is the coefficient values in the key column. So here key column is the x2 variable column. And one more thing, ck values should be greater than the 0. If ck values are the negative and the 0, we are not calculating the xp divided by ck for the respected row. So first we have to calculate the xb divided by ck for the first row, that is the S1 variable row. Here xb value is the 6 and ck value is the minus 2. So ck value is the negative. So we are not calculating the xb divided by ck for the first row, that is the S1 variable row. Next we determine the xb divided by ck for the second row. So here xb value is the 10 and ck value is the 0. So ck value is the 0. So we are not calculating the xb divided by ck value for the second row also. For the third row, xb value is the 1 and ck value is the 1. So xb divided by ck will become the 1 by 1, which is equal to the 1. So among these three values, we are determining the only one value. So we are having the only one value, that is only the minimum value. So here minimum value is the 1. For the respected row is the A1 variable row. So minimum ratio is 1 and indicated by the arrow, and A1 is the outgoing vector. Next we have to identify the common element in the key row as well as the key column. So here key row is the A1 variable row and key column is the X2 variable column. So among these two, key row and key column, common element is the 1. So 1 is we are calling as the key element. So next once again we have to construct the new simplex table, that is the first iteration table, by entering the incoming variable. Now we have to construct the new simplex table, that is the first iteration table. Here x2 variable is incoming variable into the basis and a1 variable is the outgoing variable into the basis. So we have to replace the a1 with x2 in the basis of the new simplex table and also change the CB value, that is cost coefficient value of the x2 is the 5. Next we have to apply the row operations to get the optimal solution. Before that we have to remember key element become the 1 and remaining elements in the key column should be the 0 in the new simplex table. For this apply the following row operations. Before apply the row operations, consider the R1 old, R2 old, R3 old are the row 1, row 2, row 3 in the old simplex table. R1 new, R2 new, R3 new are the row 1, row 2, row 3 in the new simplex table. So first we have to apply the row operations for the key element row, that is the row 3. So here observe key element value in the old simplex table is the 1 and also it will be become the 1 in the new simplex table also. So there is no changes are required in the row 3. So R3 new equal to the R3 old and the same values are write down in the R3 new. So that is the R3 new values are the 1, 0, 1, 0, 0, minus 1, 1. Next we apply the row operation for the row 1. So observe that one in the old simplex table its value is the minus 2 and it become the 0 in the new simplex table. For this we have to apply the following row operation, that is R1 new equal to R1 old plus 2 R3 new. So first write down the R1 old elements, that is the 6, 1, minus 2, 1, 0, 0, 0. Similarly write down the R3 new elements, that is 1, 0, 1, 0, 0, minus 1, minus 1. But we have to do the row operation is the R1 old plus 2 R3 new. So I have to multiply with the 2, that is the 2 2 R3 new will become the 1 into 2, it is the 2. Then 0 into 2, 0. 1 into 2, 2. 0 into 2, 0. 0 into 2, 0. Minus 1 into 2, it is the minus 2. 1 into 2, it is the 2. Then we have to perform the row operation is the R1 old plus 2 R3 new. That is the 6 plus 2. It will become the 8. And 1 plus 0, it will become the 1. And minus 2 plus 2, it become the 0. 1 plus 0, 1. 0 plus 0, 0. 0 plus minus of 2, minus 2. 0 plus 2, it will become the 2. Next we apply the row operation for the row 2. In old simplex table, its value is the 0. And in the new simplex table, it is also become the 0. So there is no changes are required in the second row. So that is the R2 new equal to the R2 old. So same values are write down in the R2 new also. That is 10, 1, 0, 0, 1, 0, 0. This is the new simplex table or first iteration table. Next we determine the Zj minus Cj values. First we have to determine the Zj minus Cj value for the first column, that is the x1 variable column. So Z1 minus C1, which is equal to the 0 into 1 plus 0 into 1 plus 5 into 0 minus 3, which is equal to the minus 3. Next to Z2 minus C2 for the x2 column, which is equal to the 0 into 0 plus 0 into 0 plus 5 into 1 minus of 5, which is equal to the 0. Next to Z3 minus C3 for the S1 variable, that is the 0 into 1 plus 0 into 0 plus 5 into 0 minus of 0, which is equal to the 0. Next to Z4 minus C4 for the S2 column, that is 0 into 0 plus 0 into 1 plus 5 into 0 minus 0, which is equal to the 0. Next to Z5 minus C5 for the S3 column, that is the 0 into minus 2 plus 0 into 0 plus 5 into minus 1 minus of 0, which is equal to the minus 5. So next one is the Z6 minus C6 for the A1 column, that is the 0 into 2 plus 0 into 0 plus 5 into 1 minus of minus m, which is equal to the 5 plus m. So here Zj minus Cj values are the minus 3, 0, 0, minus 5, 5 plus m. Among these values, most negative value is the minus 5. So minus 5 is the most negative value. So that is for the column of the S3 column. So S3 column is the key column and we are calling as the incoming vector. So S3 variable is enter into the basis. Next step is the calculate the minimum ratio of the XB divided by CK. Here CK is the coefficient values in the key column, that is the S3 column. And CK values should be positive values only. Here observe that when the CK values are the minus 2, 0 and the minus 1. So these values are the negative values and also the 0. So we can't able to determine the minimum ratio of XB divided by CK. So variable S3 should enter into the basis, but coefficients in the S3 column are all are the negative or 0 values. So this indicates that the S3 cannot be entered into the basis. So all the values in the key column are negative, which is the indication of unbounded solution. So solution for the given problem is the unbounded solution. Thank you.